Good evening.
Good evening.
I'm honored to be here tonight, and it's wonderful to see these people that I worked with for many years that I haven't seen in 20 years, and it's delighted to see that, like myself, none of you have aged a bit. Going to put the hook on me. I got to do this quickly. I don't have time to go through the history of C4. It's long and involved, and it's interesting, but C4 was, to me, was about the people who made it happen. And there's one person who I thought you might be interested in hearing about because nobody's ever heard of this guy. I can only think of two people in this room who may have ever heard the name. So I'll tell a little story about this gentleman who worked for Delco only for a short period of time. At that time, this was about 1965, C4 was just in the initial design stage. I'm not sure we have even won the C4 contract with 747 yet. I was working in John Sheldrick's group as a systems analyst, and one of my jobs, my assignments, was to write the equation specification for the C4 system. So that involved all the equations, everything that had to go into the computer that's buried inside a C4, the Magic 311. So when I finished writing this spec, I went over the software group, which I believe at that time was headed by Jim Thompson, who subsequently went over to Detroit. Then I told Jim, hey Jim, I got this spec, I need a programmer. He said, well, I got a new guy, we just hired him in from the Boeing company. He's a software specialist, and I think he'd work out fine for you. Well, that's the first time I met Frank Efta. So I went over and introduced myself to Frank. Frank was a very quiet, laid-back guy with a wonderful dry wit about him. So we went through the spec in some detail, and he said, okay. And that's kind of the last I heard of Frank. And sometime later, and I don't know how long it was, but it struck me as a very short period of time, he says, called me up and he said, well, let's give it a try. So we went out to the lab and he had this punch paper tape. This was before the days of floppy disks or CD-ROMs. We had a 50-foot long piece of punch paper tape which represented the first crack of the C4 software. So we went out to the software lab, and at that time, in terms of engineering, software was kind of the Rodney Dangerfield of disciplines. Our lab consisted of two workbenches sitting in an aisleway next to the loading dock on the far west end of the program of the plant in Oak Creek. We had two workbenches to work off of. We had a breadboard, Magic 311 computer, some support equipment to load the program, stuff like that. And I think we had a Carousel 4 breadboard control and display unit, and the mode select panel, which is simply basically an on-off switch. So we fired up the program, and of course we got the blue screen of death immediately, and there was no control alternate delete anywhere. But Frank worked through it, and he finally got the program to the point that it wasn't blowing its brains out, and we started the checkout, equation by equation, subroutine by subroutine. And this went on for a while. Programs were a little harder to check out back in those days with the tools we had to work with. Well, we started peeling layers off the onion and got closer and closer, and I could see a flicker of light at the end of the tunnel, and we were under a schedule problem. And Frank made an announcement one day that just set me back on my heels. He said he's leaving the company. I was devastated. And I said, Jesus, Frank, is it something I said? Did I win too many flips at the coffee machine? Well, Frank was an interesting guy. His number one priority in life was his family. He had moved from Seattle to Wisconsin because it was his number one goal to raise his family on a farm. There were a lot of farms in Wisconsin. He figured this is ideal. Well, unfortunately, with the salary he was offered when he came in, and when he started looking at the price of land, he realizes his goal was not possible. He was dead in the water. So he looked around and he talked to Honeywell up in Minneapolis, the Twin Cities. They offered him a very generous salary, but before he accepted it, he looked around at the farm prices, and the two were compatible. He had a he had a salary, looking at farm prices, there were no subprime loans in those days, but it looked like it would fit. So he tendered his resignation, and I was devastated. We had another program at the time who was working with us, but he obviously was not going to fill Frank's shoes. So as we got closer to the drop dead date when he was going to leave and head for the Twin Cities, he came to me and he said, would it help if I stayed an extra couple of weeks? And I said, oh God, please do, So he stayed, and we got a lot done. We worked long hours, got a lot done. Programs started to come together reasonably well. And then shortly before he was ready to depart, he says, would you like to come over to my place for a drink after work one night? I said, that would be great. And then it dawned on me, I said, well, you were living in an apartment while you were farm hunting. And he says, yeah, I had to give up the apartment at the end of the month, but I got something lined up. I said, well, okay, great. He said, I'm living out in Muskego right now. It's a little town about 20 miles, well, actually, where am I here? It's about 20 miles west of the plant. And I was living nearby in Berlin. So I followed him home that night. And we go through the metropolis of Muskego, and we go beyond Muskego. And I'm figuring, where does this guy go? We're out in the boondocks now. And he makes a turn on a little side road, and there's a sign that says, Muskego County Park. I'm really, what's going on here? We drive around the corner in the park, and there's a tent. And there's his wife and 3 children sitting around a campfire, waiting for Dad to come home. Well, we got a lot done in those 2 weeks. Obviously, he didn't want to go home. I don't know if his wife talked to him for the next year or 2. But anyway, he left, and progress stopped immediately. And then, thank God, Lou Richards, who I think you probably all do know, was put on the project. He picked up the ball, and very shortly, we had a program that looked like it was working. So I gave Dave Lewis a call. He was putting the hardware together. He prototype 1 C4. He was assembling that. I called him up. They were in the other end of the plant in the systems lab, and I says, how's the hardware? And he says, I've gone about as far as I can go. He says, the hardware, the power supplies are all checked out, the interface of the boards are working. And I said, okay, I got a program that might work. So I rushed up there, and this was late in the afternoon, and we loaded the tape, and we fully expected to get a massive red lights, everything short of smoke, and the damn system worked. There's a display on the pilot's display, and it's a status indicator. It tells where you are in the alignment, the leveling, the gyro compassing, all that kind of stuff. And it starts counting down, 9, 8, 7, 6, and it's going on. And not a glitch. So all of a sudden we get a ready green light. That tells the pilot that, hey, you're fully aligned, you can now go to navigate, and you can take off and go to Rome or Paris or Sheboygan or wherever you're going to fly to. So Dave and I looked at each other and said, well, what the heck? We selected the navigate mode. And we expected the system to take off for parts unknown. It just sat there. Now, for those who are not familiar, an inertial nav system sitting in the lab is not a trivial problem. The Earth is still rotating. It's sensing about 700 miles an hour. So it is not a trivial problem. But about that time, John Sheldon came in. It was pretty late in the evening, and John, in his typical, fashion, what the hell are you guys up to? And we said, well, we're navigating. And he gave us a stare. He walked over. He was a pretty quick study. He looked at the system. He looked at the Corona display and everything. And he says, I need a volunteer to stay here tonight. Well, Ollie Clement, who I'm sure most of you know, said, I'll stick around. The rest of us all headed for Breezy's Tavern across the street. I wish I could tell you who was all there that night, but it was Dave, of course, John, myself, Rudy Poklar was there, I believe he's here tonight somewhere. Dave Shipway of the Boeing Company was there, and I'm sure there was one or more customer service people who was helping us out in the lab at the time. So we all went over to Breezy's and had some adult beverages, and my mind wandered to Frank Efta. You know, how was Frank doing up in the Twin Cities? Well, as a tribute to Frank, it's 45 years later, carousels are still flying, and he's the guy that checked it out. We're living in a tent. And my hat's off to Frank tonight. Unfortunately, he can't be with us. He passed away 4 years ago. But he did get his farm. And shortly after getting to, I called him up, shortly after getting to the Twin Cities, he bought his farm. And he was one happy camper. And he loved his job. I've tried to get a hold of his wife, and I've never able to get her. I probably called her 50 times, and I'm never getting an answer. She's obviously out staying with relatives or whatever. Well, that's a little story of one of the contributors to C4. Now to something totally different. He told me he's going to give me the hook if I run over.
No, I didn't think.
But the Airbus series, we did not have any presence on any of those airplanes. And I was in development engineering at the time, and our future in the inertial business looked very, very bleak. And the reason is that the airline industry decided to change the specification for the inertial system on these new, what we call all-digital glass cockpit airplanes. And they said the system had to be a strap-down system. And what that simply means is there's no gimbal structure to keep the gyros perfectly level at all times. They're literally bolted into the box. The gyros that we were building at that time were simply not suitable for strap-down application. So we were literally out of business. Now, fortunately, we were fat and happy. We were selling a zillion C4s at the time. But if you wanted to look down in the future, we'd have no future. Well, then we got word in Milwaukee that Santa Barbara had successfully built a hemispherical resonating gyro. The HRG is a very unique instrument, and it had been worked on for starting back in the late 60s in our Wakefield facility, and then moved out to Santa Barbara. And under the guidance of Ed Loper and Art Voros, who is here tonight, and Marty Stevenson, Dr. Stevenson, they finally successfully built an HRG that worked. I don't have time to go into the details of an HRG, but it's basically it's a vibrating wine glass. And maybe you've seen some of the displays out there of the actual piece parts. And it turns out that vibration patterns wants to stay fixed in space even though you rotate the wine glass. So it has angular sensing properties, and therefore we would call it a gyro. Even though it doesn't have any spinning wheels, hell, it doesn't even have any moving parts. As I recall, it flexes about 50 millionths of an inch, something like that. It's a tiny bit. Well, they achieved success. They built a gyro, I think it was called the Dash 31 model. Not sure. So when we heard about it, we immediately headed for Santa Barbara to see what they had. And what they had was, let's see, there's the gyro. It actually all goes together. And there's three main piece parts, which you can hardly see. In the middle, you can see the resonator. Ah, great. In the middle is the resonator, and up above it is what's called forcer housing that supplies energy into the resonator to keep it vibrating. And below it is what we call a pickoff, and that goes up inside the resonator, and it reads out what the pattern is. And then the other pieces you see are actually just an enclosure. Well, when we looked at it, it looked very complex to build to us. And that pickoff housing that you see there, that thing on the bottom, towards the bottom, looked like it was going to be very difficult for us to build. Now, when this gyro was designed, it was designed for the ultimate in accuracy. For a inertial system for a commercial aircraft, we didn't need the ultimate in accuracy. We just needed a pretty good gyro, but it didn't have to be the ultimate. So the tolerances on all these parts were very tight. And the tooling to put it together was very, very tight. So we were building between 100 and 200 Carousel 4 gyros a month. And we looked at this and said, could we possibly build 100 to 200 of these a month? Well, the other, not a problem with the gyro, but the gyro was quite large. It was about 5 inches tall, about 4 inches wide. But the box size that the airlines had specified was about, like a bread box. It was about 12 inches wide, 12 inches deep, and 7.5 inches high. Even though the gyro was big, it would easily fit, 3 of them would easily fit in that box. So we said, oh, okay. We'll see what we can do about, making it producible. Well, the system, the gyro, the program was somewhat floundering. I shouldn't say that necessarily in those words, but, and about that time, Bob McMillan took over as plant manager in Santa Barbara, and in his inaugural speech, which I assume went on for hours, right? He said his first official act was going to be to cancel the HRG program. Well, we were devastated because it was our only hope for the future in commercial inertial. So Bob came to Milwaukee about 2 or 3 days later, and Jack Becker, Wayne Schaefer, and I sat down with Bob and convinced him not to cancel the program. Well, he gave us an ultimatum. He says, okay, you show me the gyros can be built within the next, I think it was like 60 days, and if you can't, that's the end of the program. So we rushed back to Santa Barbara, and we sat back down with Art Voros and Dr. Lynch. Ed Loper had just gotten married, and he was on a 6-week honeymoon. And we sat down with all the people who were trying to build the tooling. And we just slashed at the specs to try and relax everything to get this thing built. Well, we did get it built. And within about, we certainly made the 60 days, as I recall. But then we ended up building about 20 or so of these gyros, and they worked fine. Even though we had relaxed the specs, it still was an incredibly accurate gyro, even a little more accurate than we needed. Well, then we got hit with another 2x4 right over the head. Our competitors in this business, Litton and Honeywell, have developed small ring laser gyros, about the size of a package of cigarettes. Well, they knew how big our gyro was, and you need 3 of these things. So they went back to the airlines and said, we really don't need a box 12 inches wide for our little gyros. So they said, why don't you reduce the spec? And they reduced the box size to 4.9 inches. So we went from a bread box to a loaf of bread. Well, now once again, we were dead in the water. And I said, oh God, here we go again. Well, rather than give up, we went back and said, well, what can we do with this gyro to shrink its size without changing the fundamental dimensions? The gyro is called a 58 millimeter diameter resonator, so it's always called a 158 gyro or whatever. 58 is always in. So here's a little picture of a drawing of the gyro with its 3 major pieces. So if you look at that resonator, the thing in the middle, you'll see that upper stem sticking way up in the air. And that's there for a reason. It stops the resonator from wobbling back and forth in a vibration environment. And we said, well, how important is that? So we asked Santa Barbara to build us another gyro, but just cut that stem off and let's see what happens. So they cut it off, we got the gyro, we put it on a shake table, and there was some disturbance at certain frequencies as we shook the gyro, but not a showstopper. So we said, well, we've taken that gyro, which was about the size of a pineapple, and we shrunk it down now in height. We could lower that upper piece. Now we're down to the size of a grapefruit. It was still too big, but it was a start. So then we started to get a little desperate. And if you notice, I was hoping the screen would be right here. I even brought a laser with me to point at the parts, but I don't think I can do that. Ken. Anyway, on the pickoff, the lower part, you'll see there's some pads on there. There's actually 8 of them, and they read out the position of the vibration pad. On the top part, that big piece, that's the forcer housing. It has about 16 pads on it, and it's used to apply forces to the gyro to keep it vibrating, and there's other reasons for it, which I won't go into. And we said, would it be possible to take all those features that are in the forcer housing on top and jam them into the pickoff down below? In other words, we would combine the forcer and the pickoff into one piece. Now, we estimated the chance of this really working for all kinds of technical reasons was about 2%. So we decided to do a little proof of concept experiment. And this is that experiment. The resonator is sitting up on top, and we took a little hunk of ceramic material and stuck it up inside of there, and I believe it had like 32 pads on it. So all these pads had to be shrunk dramatically to make it fit. And it was a real kludge. You can see the wires hanging all over the place. Now this gyro has to operate in a very deep vacuum. So we stuck it in a bell jar, and we turned it on, and figuring that this thing has no hope of working, and it worked perfectly. This was like the Energizer Buddy. No matter what we did to it, it kept working. So what had happened then, we had the gyro now became a 2-piece gyro. There was only 2 piece parts to it, and there they are. A little stubby resonator on your left, and a pickoff housing that had a whole bunch of little pads on it. So now we had this thing, and we said, well, we still need a vacuum. What are we going to do about a vacuum? Well, this thing has to be mounted in some kind of a holding fixture or platform. So we said, well, let's just take a cube and drill 3 holes in it, stick these 3 little 2-piece gyros into the 3 holes, and then put a vacuum and suck the middle of the cube out, full of vacuum. So we started looking at that, and it looked like it was feasible. About that same time, we went over and paid a courtesy visit to Lufthansa. Lufthansa was very much a friend of Delco. They had their systems, our systems, on all their 747s. So we talked to Dr. Dieter Reichau over there, their engineering director, and he said, I really like this HRG idea. He wanted a competitor to the laser anyway. He said, I tell you what, could you build me a system in a C4 box? In other words, it looked like a C4. Put 3 of these big HRGs in there, and I'll flight test it for you. And he says, and then if you can convince me this cube of yours, this little 3-axis cube that I just mentioned, I'll show you a picture of it in a minute, is going to work, I'll specify your system on our next buy. We're the kickoff customers for the Airbus A321 airplane. This was a Christmas present. So Jack Dickinson immediately started putting together a HRG strap-down system in a C4 box. Externally, it looked like a C4. He did it in record time. He didn't mess around with any Magic 311 computer. He took the most powerful processor he could find, which was the Motorola 68040 at the time. Put in a few megabytes of memory rather than 6,000 words. Programmed it in a high-level language. I think it was either A or C. He got it over to Lufthansa very quickly. I think in terms of a prototype development, it was incredibly quick. In the meantime, we started looking at, okay, we still only have 4.9 inches to work with. The cube looked like this. Okay. Yeah, there's a little better picture. You can see there's 3 gyros. You can see those circular things. Those are the gyros. And they're stuck in the 3 faces of the cube. That's the whole platform. Now, there's more that has to be added to that. You have to put a cover over that. There's a little electronic circuit board that goes on the top of that back end of that gyro. There's a little cover, and we had 4.9 inches to work with. Well, plus the thickness of the wall of the box, less the thickness of the wall of the box. So it was we weren't quite sure it would fit. But we tried it, and that's what we ended up with. That's the box, and it fit with about a 1/16 of an inch to spare. we started off with 3 pineapples, and we ended up with 3 things about half the size of an orange. Stuck them in a platform which was made out of titanium because it's nice and light, has a low coefficient expansion. You can also see 3 accelerometers mounted on that box, and then there's way down on the bottom, that's an evacuation port. That's where you pull your vacuum and seal it off. About that time, we got the report back from Lufthansa. They had flown, this all took about the better part of a year. They had about 3,000 hours of flying on this strapped down HRG version of a Carousel 4. They had 0 failures, and the accuracy was significantly better than Carousel 4. So this was probably one of the most successful flight tests that we've ever had. Our sales department got busy, started beating on the airline doors. We got contracts with Delta Airlines for this system. We had some kind of an arrangement going with China Air. We were working, of course, with Airbus to make sure we could get on that A321 airplane for Lufthansa. And at that time, we were talking to Boeing, and they were coming out with a new version of the 737. I think it was called the Dash 500 at that time. And they were going to put inertial systems on that. And because of our past relationships with Boeing, I think our chances of getting on that airplane were very, very high. So it was very exciting. So the system got built, which we call the Carousel 444. And we wanted to keep the Carousel name, even though this thing had no moving parts. But you didn't want to, that name was well respected in the industry, so we kept it. This is what the system looked like. It was 4.9 inches wide, 12 inches long, it had 4 circuit cards, it had 0 moving parts. It didn't have any bearings, slip rings, motors, synchros, resolvers, heaters, fans, nothing that C4 had. It had 4 circuit cards instead of about 24 circuit cards. It was, I thought, one of the most elegant pieces of engineering I'd seen in my 30-some years at Delco. The system was fired up one night, almost exactly 25 years after the first Carousel 4 system was fired up. Once again, it worked perfectly. And once again, there was a party of breezies. Although breezies was now called Cliffords. And it was a lot bigger group then, and everybody was there. There was a great amount of euphoria going on because we were back in business and we absolutely had a killer crowd. Unfortunately, that all occurred on a Wednesday. Now, Delco had, about that time, had been spun off as Delphi. So we were no longer DSO, because Delco was no more. And we got put under the wing of Hughes Aircraft. 2 days after our party, Hughes came in, closed the door, put a for sale sign on the front lawn. This was a classic example of defeat being snatched from the jaws of victory. This wonderful little, we call it the Carousel 444, was the name we gave it. It was an engineering triumph that turned out to be a tragic failure, came to a tragic ending, I should say. And that's the story of Milwaukee's almost successful commercial HRG venture. Now, Art will talk about a little more successful version of the HRG that was used in space a little later. And I guess, yeah, Jack. When we worked with Boeing on the original Carousel 4, starting back in mid to late 60s, our chief contact, the chief engineer at Boeing was Jack Shaw. He was a tough taskmaster, but he was very much responsible for this success. He didn't let us get away with anything. When he saw a problem, he let us know and told us we better damn well fix it. And we did. So Jack, excuse me, I got a product. You'd like to come up and say a word? And I thank you for your kind attention.
Good evening.
Good evening.
Thanks for that introduction. Tom, thank you for inviting me. It's been 20 years since I was in Milwaukee. Last time I was in Milwaukee, Don Atwood was presenting in charge of a presentation for 20 successful years of building of the 747 Carousel 4 system. And although I was no longer on the Carousel 4, I left the program after we certified the 747. I was asked by Boeing to come back and represent Boeing for that meeting 20 years ago. Just halfway between the 40-year mark you're at now and the start of the program that John so well discussed. I congratulated Delco and the people at that time for having done an outstanding job. They went through hellfire. There were numerous problems with the system. I think back on it now, it was a really gutty move to start off with 3 or 4 instruments. Ken Fromm over there remembers the problems. And with a new computer and with state-of-the-art equipment, which had never been developed before, never been used, and on a tight production schedule. And in the end, they succeeded and did a marvelous job. I've taken the opportunity on this trip to meet some people that I haven't seen for, in some cases, well over 20 years. I'd like to mention 3 individuals that are not with us now that were instrumental in the program. Ole Clement was one, John Sheldrick was another, and Jack Becker was a third that I spent a lot of time with. And they have all passed on. And the people that I've met here, I'm sure I'm missing names, but the people that I've met on this go-around, of course, was John Kaufman, Dave Lewis, who I spent a lot of time with also, Rudy Poplar, Steve Lockman, Rich Johnson, Byron Singer, John Vanachuk, Dan Fromm, that I mentioned a minute ago, and I've missed a few names, but they were all very instrumental in making this program a success. The other people that were just as important but were unseen are the wives of these men. There were lots of long hours put in on this program, and I'm sure the families and the wives suffered during the time of development of this program because of the extreme amount of effort that was put in to make it a success. John didn't tell the full story on the HRG. It was a viable competitor with the ring laser gyro for the 777 program. We had gone to a strap-down version on the 757 and the 767. And I was pushing the industry to take a step beyond that to go to fault-tolerant equipment. And the 777 has a skewed axis system. Reduced the number of instruments, which were the most expensive part, by 50%. And I was hoping that the HRG would be a contender for that. It turned out not to be. And the ADER system was developed. Honeywell was the winner of it, and it's flying today. So I just want to say thank you to all of you people that were involved in the Carousel 4 program. It was a great example of a development program under pressure with some tough specifications in everything from performance to reliability. And you folks came through marvelously. And that's all I've got to say.
Move on to our third speaker, Art Voros, who's you all know, many of you know, retired senior scientist from Delco, Lytton, who was involved in development of spinning wheel gyroscopes from the early days, and then, of course, finished with the vibrating quartz gyros used in space today. And I'm going to let him tell the story, but the result of all that hard work is a record in space of HRG products of over 12 million hours of space flight without failure. So I'm going to let Art tell you about those successes.
Thank you, John. Listening to John's story, hearing the earlier HRG attempts and not quite making the final cut, is a sad scenario. I appreciate the effort of all the people that John related to on that program. So I'm going to speak a little bit more to where it did go, as more of a successful continuation of a program that a lot of people out here in the audience, and others that are not here, of course, worked on, and also went through a long turmoil as far as seeing it accomplish some sort of success. That didn't come easily either. John's good words about how well it could work at that point was preceded by probably 30 years of attempts to make it even work that well. And that goes to a lot of credit. Starting off the bat, we'll show how good it is right now and some of the results that are represented by Northrop Grumman's current results on the program. They own the instrument, they own the system right at this point in time. They picked up, Delco rolled over to Lytton in the inertial business in 1995, and I was part of that in Santa Barbara. And all the inertial work that was going on, which was mostly the HRG world, became their ownership. And then sometime 2 years later, Lytton sold out, or was bought by Northrop Grumman. And they currently are providing most of the performance and accomplishments that we're looking at tonight. But it goes back a little bit earlier than that. The bottom line really is shown in this chart. It's almost like the dessert story, the dessert part of the whole meal. And that is basically that, as mentioned a couple times here, the instrument is really an excellent instrument. It's currently used in a lot of space applications and satellite applications. It's a smaller instrument that John referred to, and that will be shown a little bit later about how that all happens. But it really is now the instrument of choice. And I think there's a story a little bit later in here about Lytton, who really was our main competitor. A lot of our competitors, along with Honeywell, of course, on gyros and inertial systems. with ring laser gyros, fog gyros, fiber optic gyros, and the current strap-down type gyros. And Lytton involved themselves, of course, about the HRG systems. And they currently call it, in their viewpoint, the better gyro ball. And I think that's really a realization, because we face a lot of issues with the ring lasers. Now, admittedly, all this comes in a certain time phase. You don't just suddenly make a change quickly because you like it. It takes time and effort to get to that point. And in this case, we'll go back a little bit. This is a little bit more graphical illustration about the period of time that was mentioned briefly back in the late 60s when it started in Wakefield as far as the concept for the bell jar. And if you tap one of your wine glasses, you'll hear it ring. John mentioned briefly about that, the sense of how that becomes a sensor. You rotate that wine glass in a real fashion. The pattern doesn't stay where it was, it moves backward. And that means it's a sensor. You can rotate, verify it's back to something that's rotated. That's what the gyro really does. Be it a spinning wheel, be it a laser system, which is complex, I think, or other versions. So along back in the late 60s, it started, it moved along with various milestones, as you can see in that chart, as represented by the small monkey becoming more of a large ape and finally a walking human person with some maturity. And the applications that follow on the bottom show some of the things that were done along the way, clearly by Delco in Santa Barbara, in Milwaukee, and starting in Wakefield, and continuing into Lytton, and ultimately into Northrop Grumman. Now, this is the illustration you saw already before. I won't do too much of that. That's the hardware, what we call the 58 millimeter, which is a little over 2 inches. That's the shell size. But that processing is really unique. This is all quartz, pure quartz. Not like your wine glass. This thing wants to resonate. You tap it in a vacuum, it'll ring for 20 minutes before it decays down. And it's got to be in a vacuum, as we was talking about. Anyway, so that was a lot of effort there. It took a lot of fussiness to create a wine glass type application. Wine glass is the poor name for it. It was replicated. It was people who copied it over the years. Russians got involved with it. There's other people looking to make something like this, but it never quite got all the technology. So that was an early version. At this point in time, a 30 millimeter is illustrated in the lower left corner. You can look at the size of the diamond, and that's a little shell. And that's been machined by a company previously named Speed Ring on a grinding machine. And very precise tolerance without shattering that even piece of glass. And then it's metallized, and then it's put together with the hardware that John talked about. You see the configuration there as a fire completely similar to the gyro. In that period of time when we were building the 58 millimeter gyro, and that was the size we started with, and we didn't want to change too much because we just didn't want to screw up anything before we had to. But it became obvious that the size was an issue along the way. So we said, what about something like about a half-size gyro? Well, there are applications out there besides the inertial business with aircraft and guided missiles with high accuracy about maybe tactical missiles could use something cruder. So how about a half-size gyro? Well, there were predictions by the physicists and mathematicians that it would destroy the performance of the gyro. Once you drop down a factor of 2, they thought it would be probably 10 or 20 times worse performance. Other gyros, floating gyros, laser gyros are affected by dropping their size. Well, as the chart shows, it didn't happen. It came out with good performance, very good performance, and it launched, let's go with this thing. Unfortunately, at that time, this was a period of time when we were developing it, and John was going through the machinations he described about trying to get this thing smaller and smaller. And the 30 millimeter was, in some sense, present in Milwaukee, in Santa Barbara rather, but it wasn't really that mature. And it was just the timing, like a lot of things. It was just a little bit too late in the power curve. But there were applications. You can see a couple things there. The 30 millimeter became present. We built a number of instruments. They put it together to try to see if we could work in the Hubble telescope. Now we're going to work our way into where really the initial business for this device is at this point in time. The Hubble was having clearly problems, as you all read in the papers, about the gyros were going off the deep end. They're floated gyros built by Allied Signal, gas-bearing gyros with flex sleeves that were corroding and dying. So the gyros were having difficulty. So they came out to Santa Barbara and said, how about an HRG in Hubble as a replacement? This is like 10, 15 years into the Hubble program. anyways, they built one, it looked good, it ran with a factor of maybe 2 of what the level performance wanted. But they said, no, we weren't gonna go with that. And I could imagine if I was a program manager involved with that, would you start changing gyros and major, mechanizations at that point in the program's needed at home. So it did good, but not good enough. On major vibration, this thing is just about a half a foot behind the tip of the drill went into solid rock. Vibration, heat, and everything else. Anyways, they tested that for a bit, it looked good, but it didn't really come to pass, and it probably just as well. Anyways, the instrument is basically the 3 major parts. John touched on that, I won't drill on it too much more. The hardware is quartz, metallized, bonded together. It's not a double stem device, it's a single stem, it's an inside mushroom. So that does its job that way. The system was put together. Now here, Northrop Grumman gets a little stronger. We left it in Santa Barbara in the late 90s as a device that needed some upgrading along the way to really become a high performer. There were certain Achilles heels in that jar, and one of them was, and it's always the case, helium. In this room, there's roughly 980,000 microns of air, mostly nitrogen and oxygen. But along with that, there's 4 microns, 4 parts per million of helium. And we always knew that the quartz gyro was permeable to helium. You could put helium around it, and it would go into the gyro and ruin the battery. So that was basically the problem. We thought you take the system and put it into an aircraft, and one of our competitors walks in with a bunch of helium balloons and breaks the helium balloons, that system's going to go right off the wall in a matter of sort of a few hours. So that's really not the right answer. So the issue about fixing it was not the easiest thing to do, but it did accomplish along the way. It became basically a completely sealed, metal closed instrument that sounds easy to do, but not so simple in reality. And they then called it now a 130p, 30 millimeter single axis precision gyro, upgraded performance in the electronics, a couple other things, put together a system that Northrop Grumman now calls a scalable space integrating rate, inertial rate system. We call it the SIRO, they call it the S-SIRO, basically scalable, which basically was they're putting more radiation hardening in the system for certain applications. So the system performance, when they did those changes to the gyro and a few other things along the way, in the column on the left side and the right table, lower right table, is basically how the core SIRO was re-left in Santa Barbara. And when they made these changes, you can see there was roughly 10 to 100 times improvement in performance along the way. And that really opened a lot of doors for them. I like this kind of chart. This is something that might be pointing a lot of guys that worked on gyros. You'd like to see what it's all made of when you cut right through it. And that's what this is. The color is worked out right. The gray color in the middle is all the quartz hardware with the 3 major pieces. The quartz resonator, forcer, and T12 inside and outside. That's everything that John described. Keep the thing operating. There's about 6 thousandths of an air gap between, not air gap, vacuum gap between the inside and outside of the shells. And it's wrapped around with a nice metal enclosure that maintains the vacuum. I mean, a complete metal enclosure. And as they described briefly there, they put some heaters in there. This is now, again, the gyros that left Delco and became part of Northrop Grumman's instrument package. Put heaters around it, made a better compliant mount to hold that gyro into the system. Because again, you got a quartz inside, and again, the gyro really dictates what it was in operation. The system may want to do something, but if the gyro says, we don't want it that way, do what the gyro wants, because that really is the heart of what the thing is going to perform at. So again, you wrap it around with some metal, but you put some compliant mounts on it, so whatever happens as far as expansion rates between metal and quartz, they're isolated by a nice compliant mount. So real engineering in that sense. The system there, they call scalable SIRO again, basically describes in more detail how the performance of that system runs. There's a lot of detail on that point, but at the bottom lower left, you can see they've got 4 gyros, they call them cross-strapped, again, different angles, so there's redundancy, and the system is such with the 4 HRGs, electronics wrapped around it, packaged up. Now, they probably aren't matching maybe the urine sizes on that particular system there, but they're wrapping in, again, a lot more capability for space applications. and satellite applications. And that brings us to this chart. And this summarizes basically some of the applications that are out there. Again, they're on contract with all the major satellite manufacturers. This is an HRG-based system. And that's like 50 contractors. The DoD, NASA, commercial satellites, and international satellites. And beyond that, the orbit experience and low orbit and geosynchronous orbit, high Earth orbit, they're all out there with these kind of systems in there. And in the experience factor, you can see there, and the performance numbers basically saying that they've had no failures. And I mean, this is 12 billion hours of gyro operation without failure. And they're actually saying now that the orbit performance is better than they see in test units on Earth, in test stations on terrestrial ground and in their test labs. The space missions then become probably a bigger high visibility aspect, where they're into, Leon was talking about the asteroid activities. You've got basically now the NEAR program that was actually launched in the early and middle 90s to land on Eros and evaluate some of the information there. Cassini was a rather expensive system. They're going off into Saturn, flying around the moons, and in orbit around Saturn, and actually landed a probe on one of the moons of Saturn called Titan. Deep impact, putting another pair of HRZ systems, one with the impactor hitting into the comet and watching the debris come off and collecting it on a second system called the flyby system. That was done, and that flyby system is now continuing out to another comet to observe its characteristics. Messenger, currently en route to Mercury, actually around Mercury, but it won't be in its final orbit injection until 2011. That system, they mentioned along the way, this is probably my sales pitch, the comment along the way was the mission engineers at Messenger, actually in Deep Impact, both had comments feeding back to the cyber people saying, we're not seeing your system perform. In the case of Deep Impact, they were saying they had alarm systems on there, they had alarm indications and saying there's nothing that says the system is even running. We've seen no information. And it turned out the alarms were set so high that the gyros in the system performance was so much more quieter. So they lowered the alarms back down. You can see the system was performing in a contrasting fashion. And Messenger, on its way to Mercury, there they were seeing too much noise, and they were blaming the system again, and they looked at it more carefully, and they found out that the star trackers, which were using the system to do a precision reference to the star by means of telescopes, were actually creating more noise than inertial systems. So they shut off the star trackers, and the gyros were running fine. So, a couple of interesting positives there. Fermi is a more recent application, 2008 launch. That's a low orbit, Earth orbit gamma ray telescope by Goddard. Got about a 5-year life. And Herschel, just launched in May of this year, is a unique application. That is a infrared telescope that has been launched, and is currently in station in what they call the L2 position. It's a Lagrangian position out 4 times past the distance of the moon, roughly 930,000 miles from Earth. It's a position that basically is got a null point for gravity towards it. It'll stay relatively free there. It won't be pulled toward Earth or any other place. That was evaluated by this mathematician back in the 18th century called Joseph Lagrange. He came up with 5 answers like that between the Earth and the Sun about where the positions would be that way. Anyways, this was launched there, and that's currently in station. And you can look at Twitter.com, you can check on twitter.com/ ESA Herschel, and they will give you the status of how it's going. And currently it's there. It's an interesting position because it's well away from the Earth. It's shadowed somewhat by the Earth. It will follow the Earth around the Sun, not orbiting the Earth, but orbiting the Sun with the Earth. And that's an interesting one because it will be looking at things sort of like what's happening with the source of the original source of galaxies and stars, where black holes have come from, the source of common cosmic rays. So Herschel is out there and it's going to fool your light. Not on the chart here is something that's shown up more recently. There's a thing called the James Webb Space Telescope, named after the recent NASA administrator, James Webb. It's going to be the replacement for Hubble, and it's not going to launch until 2014. When it does launch, it's going to have a larger mirror system than Hubble, and it will reach further back in space toward where maybe the Big Bang ever started. And that's going to be in the same position that Herschel is right now, at the L2 position. Herschel will be dead probably by that time. Now that's a program that's one of the contractors is Northrop Grumman. And they haven't identified all the makeup of that program, so it's still being put together. But I imagine the CSIRO, HRT-based CSIRO is going to do well. These are just some of the pictures of the mirror and the Cassini and the activity involved with it. Some of the characteristics of what the hardware looked like. Messenger on the way to Mercury and the orbit characteristics. Deep impact, the actual impact and the explosive impact and the continuation of the flyby system. Jumping into the summary, we saw some of this already. Obviously, this is based on Northrop Grumman's information. I appreciate it passing along in terms of detail of this. But it is a very interesting story at this point in the maturity of that program. So it's nice to look at that as part of people that worked on it over all those years. Dave Lynch is the primary person on that. Mentioned that Wilbur Stevenson and a variety of others, a number of them here in the audience too. And it's now a very successful program. So it's nice to see those kind of things happen. So I haven't worked on that for 10 years. It's nice to see where they've gone with it. I think the 4 decades that they've worked on this, people worked on it from a project of wine glass to a very mature gyro that you've just seen the results on. There's really a great dedication to all the people that from Delco, Lytton, and now North Dakota have worked on it and achieved all these results. So thank you.
Are you still with us? Our final speaker is Ken Reightler. Our final speaker is Ken Reightler, Vice President for NASA Program Integration at the Lockheed Martin Space Systems Company, as well as a space shuttle astronaut and pilot on STS-48 and STS-60 missions. STS-60 was the first shuttle flight with a Russian cosmonaut on board. Ken is responsible for ensuring that all NASA activities of Lockheed Martin are well integrated from a technological and organizational standpoint. He's also responsible for strategic and business management for the human space flight line of business. Today, Ken's presentation will be about the Constellation program at NASA and the Orion crew exploration vehicle that is being developed by Lockheed Martin, and why we're going back to the moon. Ken's presentation will be lively, and it has some very interesting embedded videos. When he's finished, I listened to Ken this afternoon, and we had questions from the students, well, actually it was from the adults, that resulted in some very interesting conversation. I'd like to take 2 questions from the audience when Ken is finished, and then we'll wrap up. So, Ken?
Two questions.
You could be thinking now you're going to have to.
How did we come up with that number?
I will, because it's getting late.
Well, I want to thank you very, very much for your kind invitation to join you today. This is a real treat for me to be in the room with so many experts in the field of navigation and those that have contributed so much to our space program and the success that we've But I gotta ask, ladies, by show of hands, how many of your husbands actually stop to ask for directions when they get lost? I thought so. That's the way navigation experts usually work. Well, you know, last year we celebrated the 50th anniversary of NASA. It was a very great celebration, a lot of things to really enjoy and to celebrate and to relish in. This year we're really enjoying a 40th anniversary of a very significant event. It's something that I think impacted millions of people around the world. It was a realization of a dream that many people shared, demonstrated great courage, great innovation, great creativity and dedication. It won awards from a lot of different organizations, got great renown, and of course we're talking about Sesame Street. Sesame Street started 40 years ago this year, and it really did make a huge impact on all the parents in the room, I'm sure. It made our lives a lot better. No, of course I'm talking about the landing of Apollo 11, first landing of humans on the moon. This also was a very significant event. Much has been written and said lately about this event. I'm sure that you've read a lot in the paper and Time Magazine, etc. You've probably seen it on every news channel and Sunday morning program. So I'm not even going to try to compete with all of the wonderful words that have been said about this great event. It certainly was a tremendous technical achievement, but it was also, I think, an accomplishment of spirit. It took intelligence, vision, skill, determination, and a lot of courage from a lot of people, including all of you. It also took a lot of money. $180 billion of 2009 money, $150 billion to get it developed, and another $30 billion to get it operated and flown. It took a lot of people, 400,000 people around the world, 20,000 companies, and thankfully one of yours was one of those companies, and for that, I, NASA, and the world, thank you very much for your contribution and being a part of that great accomplishment. Much of was made about this being the space race against the sun. There's no question that the geopolitical climate had a lot to do with what allowed us to funnel those resources, focus our attention, and really commit ourselves to being able to accomplish this great feat. But it's really you go back and research it, which I did a lot for last year. I gave a lot of speeches about NASA's 50th anniversary, and so the history of that was really based on Kennedy's realization and recognition of how much people really got excited about the space program, and how he could take advantage of that attention and that excitement to be able to promote the spirit of the United States and to really galvanize the forces that we need to become a truly great country. Of course, when he did that, it really changed the world for a lot of people. Many of you in this room certainly did for me. When Apollo 11 landed on the moon, I was a brand new plebe at the Naval Academy. I was 3 weeks into a 7-week, very intense indoctrination program we call Plebe Summer. For those of you that are familiar with that, I was not sure I was even going to survive the summer, let alone go on to graduate and do something later on. But to me, having the opportunity to see this great historic event, it's the first time all year, in fact, we were allowed to watch television. We were allowed to kind of gather around little small black and white TVs and witness history in the making. And it really kind of inspired me to go learn more about these people that were making history. What was where did they come from? What did they study? What were their backgrounds? And I found that a lot of them were just like me. They were in military schools and academies. They were thinking about being pilots. They were aerospace engineers. And for me, it kind of laid out the roadmap on what I needed to do to be able to accomplish my dreams. And so, because of that, I'm very grateful. But the cost of doing that was very high. And in fact, the cost was the lives of 3 Apollo astronauts. The crew of Apollo 13 almost paid with their lives. But what they did was, I think, well above and beyond the call of duty. But the people that were getting those attention, and the people today that still get their attention, being those Apollo crews, is such a small story of what really took to make this all possible. And the people that were really behind all of that were the people behind the scenes, the people that were doing that hard work, spending those 20-hour days to make all that possible, like all of you. And because of that, I think it's really important for us to recognize your contribution. And while all went very well on Apollo 11, the landing on the moon, we all recognize that space is a very risky place, a very dangerous situation. And this clicker's not working anymore. Could you do it? With your help, we're going to get moving along here to the next scene. The point is that it went very well, but it could have gone quite otherwise. So Tom's now going to do the magic. What a terrible feeling. Well, I really enjoy looking at the past and looking back, but I really enjoy more looking forward. And what I'd like to really spend some time tonight talking about is what is the plan in the future? Where are we headed? What is it that lies ahead? This slide really captures what the President laid out as the vision for space exploration. It was then acted upon by a Republican Congress, and then next acted upon by a Democratic Congress that enforced this as the law of the land. The plan is to fly the space shuttle until we've completed the International Space Station. As you know, we have a crew on board right now in orbit, helping to do the next stage of that assembly. We have 7 more flights after that. But once that's complete, the space shuttle will be retired. That should be about the end of 2010. While they're doing that, we're going to design and develop the next generation of spacecraft to be able to take us beyond low Earth orbit for the first time since Apollo 17 came back. Orion is the crew exploration vehicle, the vehicle that's going to replace the space shuttle to allow us to do that, and we intend to fly that no later than 2015 with a target date of going back to the moon by 2020. All those dates are really driven by money. And if you think about it, the height of the Apollo program was taking about 4.5% of the federal budget. Today, NASA's total federal budget is about 1/2 of 1% federal budget. So with a lot more money, we could be doing this a lot faster than we are today, but that's where we are. And finally, we're going to be using this as Tom mentioned, my experience with the space shuttle, using that to kind of bridge the gap, bridge the boundaries between Russia and the United States. We're going to do this in a big way between all of the international countries in the United States. Now, if you look at Orion and you look at Apollo, the two look very similar. There's very good reason for that, but in fact, if you look a little closer, there's a lot of differences. For example, in Apollo, the moon was the destination. In the engineering business, if you're given very good specifications, if you're given good requirements, you can do really good work. In the case of Apollo, it was very clear. Where? Moon. When? In the decade. And that's about as good a requirement as you can possibly get in this business. We don't have quite as tight a requirement, but what we are looking at is not a destination, but in fact, using the moon as a stepping stone, proving ground, allowing us to go to other places within the solar system. Apollo was designed for 3 people, only 2 of whom would go down to the surface of the moon. Orion is designed for 4 people to the moon, 4 people down to the surface and back. It's also designed to carry as many as 6 people to and from the International Space Station. Apollo had a 3-day mission to the moon. It's hard to believe that you could get to the moon in 3 days, but that's all it takes. In fact, a round trip is only about a week. Orion is designed for about a 6-month mission to the moon. It's designed for a 6-month, 210-day stay on the space station. And finally, we're designing Orion to go anywhere on the moon, anytime, and be able to come back from any place on the moon anytime. If you know a lot about orbital mechanics, that's a really hard thing to do. Apollo was really focused on the equator, really thin band around the front side of the moon, the lit side of the moon. I don't need to tell this audience the benefits of space exploration, and there's certainly much more than what's captured on the slide. But space exploration is important to all of us for a variety of reasons, not the least of which is inspiring that next generation of scientists and engineers that we all care about so much. We really have to start kind of from scratch with in terms of rebuilding our capability to go beyond low Earth orbit from where we are today. We needed new rockets, we needed new spacecraft, we needed different kinds of vehicles than we have today to be able to get to the surface of the moon and up. And all of these are in various stages of development. Together, collectively, they're called constellation programs. Each individual one is a project. Orion is a project. For example, we had to design new rockets to carry Orion. But rather than starting from a clean sheet of paper, given the budget constraints that I mentioned, we tried to utilize as much shuttle technology as we possibly could. So what you see as far as lifting Orion will be a stretched version of the solid rocket boosters that we're carrying today on the space shuttle. The larger cargo carrier will also be 2 of those stretched boosters with a stretched external tank, just like we're using on shuttle today. Orion is using a lot of the same components. For example, its main engine is the same essentially as the orbital maneuvering system engines we have on the space shuttle. So we also had to build a Earth departure stage to be able to get us out of low Earth orbit into the lunar orbit and back. We also had to build a lunar lander that will take us down to the surface and back. Lockheed Martin has been selected by NASA to be the prime contractor for the Orion crew exploration vehicle. We are well down the road of developing that. We are right now approaching our preliminary design review. But unlike any other preliminary design review I've ever been associated with, we're much farther down the road in terms of building and testing flight hardware. And I'll show you a little bit of that in a minute. Orion is made up of 4 parts. The first part is this pointy thing that's sticking out the top. Just to give kind of reference, the diameter of that long, pointy object is about 3 feet in diameter. It's a big, big object. It's about a 5.5 meter diameter spacecraft. It looks a lot like the Apollo command module, but in fact, the crew module has about 2.5 times the volume of what Apollo did. The purpose of that thing that sits on the top with the funnel is to protect the crew module on ascent, but also to allow it to have an escape capability. Think of this as an ejection seat. If you want to get away from the rocket at any point in the ascent, this is the way to do that. And we'll show you how that works in a minute. Of course, the crew module that carries the crew and pressurized cargo, right behind it is the service module that carries all the tanks and electronics and solar arrays that provide electrical power. Look at those big round things, kind of looking like Mickey Mouse ears. That's what converts the sun's rays into electrical power that we use to propel this. And we'll see those in action in a minute too. So I think what we're going to see in a minute is a demonstration of what this launch abort system acts like. What is Orion intended to do? Orion is intended initially to support the International Space Station. providing crew transport of as many as 6. Right now our requirement is 4. Out their back is supposed to stay on orbit while the crew is on the space station, acting like a lifeboat in case they have to evacuate. It's also, of course, intended to be able to deliver cargo if needed. The NASA Orion team is sort of delegated around the country at the various NASA centers. We also use some of the military testing centers. And the Lockheed Martin team has similar kinds of placement. Some of those are at NASA centers, but also taking into consideration Lockheed Martin and our industrial partners like Honeywell and Aerojet and Hamilton Sunstrand and USA, their locations around the country as well. This is the solar array deployed, just to get an idea of what that looks like.
Under gravity, we have to lift up rate. In space, there will be no rate, no gravity, so it's a different kind of deployment. What's going to happen now, pretty close to the end, there's 2 just kind of like door latches that will, the tape will pull it in, there's tension, the latches will grab it and hold it in place. So it'll be latched down and in place. Now it's able to, all the cells are out, the sun shines on it, and it'll start generating electricity.
So the point of this is that we are building a lot of hardware. We're testing a lot of that hardware. It's being in a position where we can start flying it right now. So we're well down the road in this program. It's no longer just a bunch of view graphs or PowerPoint presentations. The next 2 videos will show tests of part of that, the launch abort system, the ejection seat that I mentioned. We'll see 2 tests of the separation motor first, and then a test of the abort motor. My lights on fire and explosions go off. Finally, we'll take a look at the abort motor. The abort motor is what actually pulls away the command module from the spacecraft, or from the rocket, separates that. It's about 500,000 pounds of thrust. There's a good reason why they test these motors way out in the desert. Our first test of all of these systems as they come together, these 2 systems along with another system that's in that spiky thing that actually controls the attitude will be done later this year. All the hardware is coming together. It's going to be tested out in White Sands, New Mexico, and we're going to put it on the ground, simulating an abort right from the launching pad. So think of the rocket and the crew and the Orion sitting out there, and then suddenly the crew decides that they need to leave, right off of the launching pad before the rocket actually launches. That's what we're simulating. That's what we're going to test in full scale later this year, and it'll look something like this. been told by the test team that they will not have that music playing in the background. This test. The point of all this is to get ready to do our mission. And the mission, of course, initially will be to go to the International Space Station, but what we really got our sights on is going back to the moon. So I'd like to show you now a video that sort of captures in short duration that trip to the moon. It won't take 7 days, like I told you. It won't even take 7 minutes. What you'll see, of course, is initially the launch of Ares 1, which is the rocket that'll have Orion on top of it. You'll see it go through its first stage and separation and into orbit. And then secondly, we'll launch Ares 5. It'll carry up the Altair. You'll see it go through its staging and into orbit. And then finally, the two will dock in orbit and then start the journey onto the moon. They'll arrive in lunar orbit. The crew will transfer over to Altair. We'll then go down to the surface, and when they're completed, they'll come back up to Orion. They'll transfer back in and make that short 3-day trip back to the Earth. And unlike what we're doing in the desert, we're really going to be landing in the water. As a Navy guy, I really like that idea. So and you'll see that demonstrated on this video.
Launch readiness for emcee, ETC, DC go, FTS go, GNC, go. Ignition, we have ignition, we have
docking with Altair. It's sitting on the top of the Earth departure stage. Once they're connected, then we'll fire the Earth departure stage to leave low Earth orbit and head on to the Earth. Crew is now transferred over to Altair, the lander. All 4 people headed down to the surface, leaving Orion all by its own up there in orbit. After a very short mission on the surface. back in the ascent stage of Altair and fire off to go back into orbit to rendezvous with Orion. Crew then transfers into Orion, leaves the ascent stage, and then begins the transition. Once in Earth orbit, we separate from the service module, begin the re-entry through the atmosphere. It's really not that rough, but it is kind of tough. So the designated landing spot is right between the Channel Islands and the coast of California. Nice smooth Navy landing. And unlike this shows, we're not going to have a helicopter picking us up like we did on Apollo. We're going to have a ship there that's going to crane them aboard. Not nearly as wonderful a flight as Apollo. Unlike the test mission, this mission we definitely will have that really cool rock and roll music playing. We're going to need a lot of new people to make this whole thing work. So we are focused on the next generation of explorers. Believe me, we have some wonderful young engineers and scientists working for us on this program. Some of the best and brightest of anybody that I've ever seen. The future is in good hands. With that, I'd like to say thank you very much for this great opportunity to share what I think is one of the really memorable kind of mile points in recent memory in terms of this moon landing of Apollo 11. I'm really glad to have the opportunity to share this really remarkable time with all of you. And I am going to ask Tom to select the two questions, because I'm not going to be held responsible.
Let's see, who have we got with hands up there? I see one hand right there. Let's try that.
Could you tell me why no other country is trying to go to the surface of the moon?
Yeah, the question for those that may not have heard it, why has no other country tried to go to the surface of the moon? And the question, that's a really good, easy question to answer. The answer is that there have been other countries that have tried and have succeeded in going to the surface of the moon. The Russians beat us to the surface of the moon with a robotic lander. They were the first people to land on the surface of the moon. But they also tried and failed to land people on the moon. They have a very, very active program to be able to take people to the moon, and unfortunately, due to a set of very bad engine-related accidents, didn't make it. Once we made it there, they decided that it wasn't worth continuing on with that and changed course and decided to then pursue a path of long-duration spaceflight, which we were as well in Scotland, but on that race to space, they beat our pants off. So yeah, there have been, and in fact, right now, today, other countries have active programs in place to be able to put robotic landers on the moon as well as humans on the moon. China comes to mind, and India has announced recently their intent to do the same.
Okay, I'll allow three questions. One from the middle, one from over there, and one from over there. I see a hand up over here.
Yes, sir.
If I understand correctly that the space shuttle program will terminate approximately 2008. And Orion is not going to be operational until 2015. What happens to the space shuttle for 4 years to the space station for 4 years?
Yeah, the question is, if the space shuttle ends in 2010 and Orion doesn't come online until 2015, what happens to the International Space Station in the interim time? The fact that we will have a 5-year gap between the period of time where the United States will have its own ability to fly crew members in space is very troublesome. It is something that none of us like. It's a fact driven by, again, budget that we were forced to do. We initially delivered a plan in which we could have had Orion flying by 2013. However, that right now Orion is not the pacing item in that schedule. There currently, as you probably have heard, President Obama has asked Norm Augustine to head up a commission or a committee to be able to look at what is the plan, what is the future of the human space program. And I think that was a very wise thing to do. Certainly something NASA has done probably every 2 or 3 years anyway. But at this juncture, I think it's a very good time to do that. And one of the things that they're looking at is, are there other options to be able to reduce that 5-year gap, make it less long between the time that we have an opportunity to fly our own astronauts. But in the meantime, the current plan is that we will continue to fly the International Space Station and to provide transportation for U.S. crew members as well as international crew members. We will rely on the Russians to do that. Is that a desirable thing? I would say most would say no. The Russians certainly like it. They're making a lot of money on it, but from our perspective, we prefer not to do that. However, it's not outside of the reasonableness during the time of after the Columbia accident, when the space shuttle was grounded for 2.5 years. We continued to operate and man the International Space Station, and Russia, during that time provided that transportation. Today, even with shuttle flying, all of our crew members, including U.S. crew members on the International Space Station, are trained, and some do also get transportation up and back from the Russians. The Russian Soyuz vehicle today provides 100% of our lifeboat or crew rescue capability if we were to have to abandon the space station because of depressurization or fire or some other calamity. So, is this outrageous? No. This is something we're very comfortable with. We do it all the time today. We have a lot of experience with it, but it's certainly not desirable. And so, all of us would like to decrease that gap, get back in the position where the United States will have its own organic capability to fly our astronauts and any astronaut we choose from any other country on our own. That's the crew side of that story. The cargo side of that story is something that has been planned all along, and that is a mixed fleet of a lot of different vehicles, some from Europe, some from Japan, some from Russia, some from the United States, to provide the cargo capability to keep the space station flying.
Okay, can we get one more question from this side?
Yeah.
Oh, wait a minute.
He's a ringer. He's a Lockheed Martin employee, so don't.
Should I shouldn't let him do that?
No, I'm sure his question will be really hard.
Oh, well, let's do that.
Yeah, that's good. John?
All right. Why would you put a crew on the moon without leaving one in orbit like you did on Apollo?
Yeah, the question is, why would you put 4 people on the moon with nobody at home up there in your spacecraft? Why wouldn't you leave somebody behind? And that's a very good question that's been debated hotly within the community. A lot of the Apollo guys think we're crazy. Why would you possibly do that? But when you go back and look at it, in none of the Apollo missions did the crew member who was left behind, have to come to the rescue, come to the, save the day. Him being there really didn't make or break, a mission. And so what it really comes down to is our architecture, our concept of operations for working on the moon and doing the science and the exploration that we want to do on the moon really is based on doing spacewalks and doing space EVA. And we do those with teams of 2 people. And so what we'd like to do is get in a rotation where you have 2 people out, 2 people in, and every other day you swap. And so by having 2 teams of 2 people, you can get the most out of your time on the moon. It doesn't work if you have 3. We can't expand the capabilities because of logistics and stores to go to 5. In other words, you can't keep somebody on the Orion and let 4 people go to the surface. It just doesn't work out in terms of how much food, how much oxygen, how much water do you need to be able to maintain. And it's also, there's a power consumption part of that equation as well. So there's there's a lot of people who agree with you, John, that would seem to be a good thing. However, none of us can convince ourselves that the trade-off right now is worth it.
Okay, I think we could do this all night long, because I know you're...
Maybe you could.
No, I know you're willing to answer questions, but I think we should cut it off at this point. It's almost 10 o'clock. I thank you for being as patient as you are. We have a little bit. We have 3 things left, but first of all, I want to thank Ken for coming. Maybe you can explain what this little video is, and I'll run it.
As you probably know, there was a large gathering of people in Washington, D.C. on Monday night at the Air and Space Museum to celebrate this historic moment. And in recognition of that event, they brought together all the members that are living, Apollo crew members, as well as all 3 of the Apollo 11 crew members were there, and John Glenn. 2 surviving original Mercury 7 astronauts, Scott Carpenter and John Glenn, were there as well. It was really a fabulous night. But in honor of that event, NASA put together a short video that really captured kind of the highlights of Apollo 11. And because of, and in recognition of your contributions to that historic flight, I wanted to bring this down here and share it with all of you.
15 seconds, guidance is internal. 12, 11, 10, 9, ignition sequence start. 6.
Feet down 2.5, pick up some dust, face down, hold forward, just under the right level, 30 seconds forward, contact light, okay, engine stop, we copy you down, you go, Houston, tranquility base here, the Eagle has landed.
Okay, Neil, we can see you coming down the ladder now.
Okay, I just checked, getting back up to that first step, it's, not having collapsed too far, but, it's adequate to get back up.
Here we go.
Pretty good slow jump.
Buzz, this is Houston. F2, 1/160th second for shadow photography on the sequence camera.
Okay. At the foot of the ladder, the left footpads are only
range as you get close to it. It's almost like a powder. Ground mass is very funny. And step off the limb. That's one small step for man, one giant leap for mankind. There you go. Maybe I want to take over the thing. A little more. And another inch. There you got it. That's a good step. Yeah. And a 3-footer. Beautiful view. Isn't that something? Magnificent sight out here. Magnificent desolation. For those who haven't read the plaque, we'll read the plaque that's on the front landing gear of this lamp. There's 2 hemispheres, one showing each of the 2 hemispheres of Earth. Underneath it says, "Dear men from the planet Earth, first set foot upon the moon, July 1969, indeed. It came indeed for all mankind, and as the crew member's signature, and signature of the President of the United States."
There's still one more piece of business to tackle. The reunion in 2014. If it's held, it will be in Santa Barbara. Yeah, based on our aging and thinning ranks, it may be too large an undertaking. I don't know. But I understand there's a committee set up to organize that reunion. Tom, to me? Yes, it was. And since nobody else from Santa Barbara volunteered, and I left the baton at home, I'm going to pass you the flag. And you and the committee that you will recruit can decide whether we do it and how we do it. But if you decide to do it, you can be sure that there will be a bunch of people from Milwaukee that will come and join you.
Well, thank you, Tom. And I just want to say, I want to thank the Milwaukee Committee for doing all of this wonderful work. It's been a great 2 days. We talked about miracles, and now I'm going to challenge you with the biggest miracle that we face and you've ever faced, and that is stay healthy for the next 5 years. And if you do, save your pennies also between now and then so you can all come to Santa Barbara, and if you're all healthy and are there, we'll have an Apollo 45 anniversary.